And you couldn't hear me because my microphone was off. Now it's on, hopefully. And you couldn't hear me because my microphone was off. So, I'll talk a little bit about the midterm in a couple of minutes. In the meantime, does anybody have questions? It looks like there's about 20 seconds of latency, so it takes a while for my words to reach you, and then probably a few seconds for your questions to reach me. When will the submission server be up? As soon as I'm done making the tester. Hopefully that, I don't know, with a little luck I can get that done tomorrow, at least for a beta version of the submission server. In the meantime, there is test code that comes with the assignment that you can try out. I think you kind of know the deal now. You should be able to run tests on data structures whose size becomes up to 1 million, 10 million, 100 million, and those tests should run in a few seconds, if even that much. Does the server keep the highest grade or the latest grade? There was some confusion about that. The server keeps everything that's ever done. So for instance, for assignment 1, there were over 12,000 submissions of assignment 1. Everybody gets to keep the highest grade that they got on any submission. The thing to be careful of with that is it means that every submission that you do, while it may not count in terms, like, it may not hurt you in terms of grades, it means every submission could count in terms of grades, which means every submission is checked for things like being a copy of someone else's submission or being a copy of something that was taken from online. How many questions will we have? Can we go back for the test? Typically there's somewhere around 30 questions on these multiple choice midterm exams. I'm not sure what you mean by go back. The test takes place for a specific hour and 20 minutes, except for some people who have some extra time allocated to them. But there's no taking a break and coming back later. You write it in that hour and 20 minutes. It's during class time. No, assignment 2 is due on the server, as always. Can we skip to question 2 and go to 3 and go back to 2 again? I have no idea because I've never done this before. I'm hoping that the testing apparatus on CU Learn is not that useless that you have to answer a question and can never go back and look at it. And I mean, CU Learn is backed by Moodle, which is generally fairly broadly used, and so I hope it's not that crappy. We'll see. What topic will be included on the midterm? Everything up to and including the lecture on Friday. Okay, so Kate says that on CU Learn we can set it up either way. We'll set it up not to make life deliberately hard for you. You get to look at a question, think about it and come back to it later if that helps. Okay, so then sounds like whoever set it up for 2401 selected some flag that didn't allow you to go back. Hopefully, well, definitely we won't do that on purpose. So don't panic about that. Okay. All right. So midterm exam is next Wednesday, October 14th, during class. So that means 2:35 to 3:55. It's an hour and 20 minutes. Don't stress too much about this. The exam is only worth 10% of your final grade, which you think, oh, that's a huge amount. But it's a multiple choice exam on CU Learn. If you've absorbed this material even a little bit, that usually means that of the 4 possible options, you can reduce it down to two reasonable ones. And then you could toss a coin and still get half the questions right. Okay? So really, it's 10%, but you should be able to get 5% almost with, if you paid any attention at all. So really, in this midterm exam, what you're fighting for is 5% of your total final grade. Okay? It's not something you should stress about insanely. If you want some practice, go to the course webpage where there's a sample midterm from previous years. There's a version of that thing which has a solution, and there's a version of it which doesn't have a solution, so where the answers are circled and one where they're not. Try and do the version that does not have the solutions. But while you're doing it, I mean, take your time. Don't time yourself the first try. For each question, don't just guess the most likely answer. Really understand why you're picking a particular answer. And if you've narrowed it down to 2, don't just guess one at random. Really try and solve those questions so that you not only can evaluate yourself at the end, but you can also really understand why, what the correct answers are. Check it against the solutions that are provided. And if you still, feel like you need to know more, then go through each of those questions and think, well, if I had to make my midterm this year, how could I take this particular question and change it a little bit so that it's not exactly the same? And then by making that change, what would the answer be? So by thinking about those kinds of things, you'll already get a pretty good idea of what the exam is going to be like, but you'll also get a much better understanding of the material. So if you think about how you would ask somebody else about these things, then it means you have to understand it yourself. I already answered the question about the marking server. It'll be ready as soon as I can get it ready. Right now I have to deal with making midterms for this course and midterms for the other course that I'm teaching, which is different than every other year that I've previously done them. In particular, for the other course I'm teaching, we have hundreds of questions to enter into to CU Learn and test that they actually show up correctly, which is non-trivial because they're mathy questions, so there's equations in them. Aren't we doing skip lists today? Yes, we're doing skip lists today, and indeed tossing a coin is a good analogy. So there's the information about that. I'll leave it up there as long as I reasonably can until I need that space on the board. So today I want to talk about something really cool. So this is a family of data structures, and the generic name for them, let's say, is skip list. And it's a data structuring technique, and you can use this technique to implement sorted sets. We'll see that today. And you can also use it to implement lists. And the lists that you get from skip lists have performance guarantees that are actually, in many ways, in particular if you want to do random access to elements in your list, including adding and removing things near the middle of the list, not near either of the ends, skip lists outperform anything that we've seen so far. Okay? They're also a beautiful example because they are a data structure that internally uses randomness. So the way skip lists are fast is that they actually do internal coin tossing. And that makes them, well, it allows them to be very fast, but more importantly, it allows them to be very simple and easy to understand how you implement them. So they're somehow easy to remember. There's no complicated rules involved in them. In fact, the algorithms are all quite simple. The only thing that's maybe difficult or difficult for new people or people who don't have the certain math background is when we analyze them. So when we would try and prove that skip lists are fast, then that requires a bit of probability because they're a randomized data structure. So this class, we will basically, I'll show you skip lists, how they work, and we'll push everything onto one theorem about skip lists, in particular about something called the search path in a skip list, that hides all of the randomness, all of this sort of difficult part, and we'll cover that difficult part on Friday. Okay. So first, let's think of an easy way to a sort of generic version of skip lists. So one way to imagine a skip list is you start with a list, we'll call it L0, and it's a list of length n for some integer n. Okay, so imagine those are the items in the list. I don't want to draw anything in there just yet. I don't want to say what the items are, but these are the elements of the list, or if you like to think of it, you can think of it as a singly linked list in which these circles that I've drawn here, they're the nodes of the list. So you can even imagine there's, pointers from each node to its successor in the list. Okay. So that's a list L0. And now what you do is, for each item in this list L0, you toss a coin. So half the time the coin comes up heads, half the time the coin comes up tails. If the coin comes up heads, then you take that item and you do what we call promoting it. So you're going to make a new list L1, and the list L1 will contain only these nodes where the coin toss came up heads. Okay? So maybe the first coin toss comes up heads, so this thing gets promoted. Okay? Now, the second coin toss, maybe that comes up tails, so this one stays. It won't participate in L1. The next one maybe also comes up tails. You don't know. And then maybe this one comes up heads. So it gets promoted into L1. And then maybe you actually had two heads in a row. So this one gets promoted into L1. Then maybe a tails again. Then maybe heads. And then tails, tails, heads. So from L0, you did this experiment. For each node, you tossed a coin. If the coin came up heads, you promoted that node up into L1. So in general, the list L1 contains a subset of the elements that are in L0. And now, two things could happen. Maybe every coin toss came up tails, so there's nothing in L1, in which case you stop. Or, as in the example here, not all of the coin tosses came up tails. Actually, in this case, 5 of them came up heads, in which case you're going to repeat this. Starting with L1, you're going to make a list called L2. So that means you toss a coin for this one. It either comes up heads or tails. Let's say that it comes up tails. You toss a coin for this one. Let's say that it comes up heads. You toss a coin for this one. We could say, oh, maybe that one also comes up heads. And then maybe here we got tails. Here we got heads again, let's say. And you connect these things into a list. So notice here we lost the first element of the list, so the thing kind of doesn't start in the same place anymore. We'll fix that in a second. So that was L0, L1, here's L2. And L2, again, it's not empty because some of those things came up from L1. So we're going to do the same process with L2. We're going to make a list L3 by coin tossing. Now maybe here we get something like tails, and then heads, and then tails. Now there's only one thing up here in L3. We're going to do the experiment again. We're going to toss a coin for this one thing, and if it comes up heads, we're going to make a list L4 that only contains this one thing. Here, to make life easy for us, I will say imagine that it came up tails. So there is no list L4, there's only lists L0, L1, L2, and L3. And now once we've done that, it's inconvenient for us that these lists don't start at the same node. So we'll introduce a new node called the Sentinel. And the Sentinel is going to be the first node in every one of these lists. Okay. So there, and there. Okay. So that's the way to think of a skip list as obtained by doing coin tosses, and starting with a list with n nodes and doing coin tosses in this order. And you can convince yourself. So I did it by scanning the list L0 and doing all the coin tosses to decide what goes into L1. And then scanning L1 to see what goes into L2, and scanning L2 to see what goes into L3, and so on. So that gives me a list. But you can convince yourself that, well, that's no different than if I had gone, approached it a different way and said, what I will do is I'll start with the first node in L0, and I'll toss coins until that coin will come up heads some number of times, 0 times, 1 times, 2 times, until the first time it comes up tails. So for example, here, for this node, I tossed the coin, it came up heads once, and then it came up tails. So the number of times that it comes up heads tells me how high up this node is going to go, right? Here it came up heads once, so it lives only in L1. But this one, when I tossed its coin, it came up tails the first time, so it only lives in L0. This one also only lives in L0. But this one, you can imagine doing the coin tosses that come up heads, heads, and then finally tails. So there were 2 heads before the first tails, so it'll go all the way up to L2. And this one here even had heads, 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 tails. So it went all the way up to L3 because there were 3 heads in its sequence. So if you think of the coin tosses from a point of view of a particular node, it's a sequence of 0 or more heads followed by a finishing with a tail. Stops at the first tail. I don't think the midterm was ever on a different day. I think the midterm was on it had a range of days, a week, and so this is the day in that week. It's a useful day because it allows both of us to write the midterm on the same day, both sections, and it also means that both sections have had the same number of classes before the midterm. Okay, so that's the definition of this thing, what a skip list looks like. And the most important thing in a skip list is, the most important thing that we study with skip lists is something called the search path. Okay. So the search path is for a particular node in L0. So let's pick our favorite node in L0, maybe this one. Okay. And the search path always starts here in the highest list at the sentinel. So the sentinel appears in every list, including the highest one. So the search path starts here, and then it follows a very simple rule. It's either going to go to the right into the next node in the current list, or it's going to go down into the list below. And the rule that it follows is it looks to the right, and if that node to the right is either the one I'm trying to get to, or it's past the one I'm trying to get to, then it will go down. So here, if I look to the right, I'll see this node, which is past the one I'm trying to get to. So the rule says that I should go down. Here, if I look to the right, I see this node, which is also past the one that I'm trying to get to. So the rule says that I should go down. From here, if I look to the right, I see this node, which is before the one that I want to get to. So I go to the right. From here, if I look to the right, I see something that's too far, so it's past the one I want to get to. So I go down. From here, if I look to the right, I see something before the node I want to get to, so I go right. And from here, if I look to the right, I see the node that I want to get to, and the rule says that I should go down then. So I don't actually go to this node, I stop at the node just before it, and it's always going to be the node just before it in the list L0. Okay. So the search path for a node starts at the highest occurrence of the sentinel and uses this greedy rule, go to the right or go down, and you go to the right as long as it doesn't pass the final node you want, which is the one that's just before the one you're trying to get to. Okay? So if this is X, a node in L0, this red thing here, this is the search path for X. And don't forget that the search path for X actually stops before X. So it stops one node before X. Why would it stop one node before X? Well, we'll see why that's useful in a second, but the main thing is, as I've drawn it here, I've drawn these as singly linked lists, and you may have remembered from the discussion of singly linked lists that if you want to do anything useful to a node, it's not actually a pointer to that node that you need, it's a pointer to the one that comes before it. So that's why we couldn't delete, for example, from the end of a singly linked list, even if we have a pointer to the end, because in order to do a deletion, we actually need to know the node that comes before it. All right, so another quick example. if I want the search path for this node, it also starts up here at the sentinel, looks to the right. That node is before this one, so it takes that step. Here to the right, there's actually no place to go, so it goes down. Here to the right, that takes us too far, so it takes us past where we want to go, so it goes down. Here to the right, it takes us to the node that we actually want to get to, but the rule says we don't go, or it takes us to the node that we're getting the search path for, but the rule says we don't actually want to go to that node, we want to go just before it. So we still go down. Here we are allowed to take the step to the right, and here's where the path would go down, but it stops here. Okay. So this is the search path for maybe this node Y, and it stops right there. All right. So make sure you understand that now, because it's the most important thing about skip lists. Now, I said that I was going to write a sort of theorem about search paths, so statement about this search paths that was going to hide all of the difficult parts of the analysis. And here it is. For any skip list L containing n elements in L0 and any node x in L0, the expected length of the search path for x is at most 2 log base 2 of n plus a constant. In fact, we'll see, depending how carefully you do it, you can show that that constant is maybe 4 or 6 or 3. But that's not important. The important part is this 2 log base 2 of n. So this says if we have n elements in L0, and I've built a skip list using this coin tossing rules to build it, then the expected length of the search path, so this thing here will define expected value next class, and if you're taking 2804 now, you'll see it next class actually as well. And if you're not taking 2804 now but have taken it before, you know it already. And if you're in neither of those situations, then I'm not sure. You'll get a definition next class. At least a good enough working definition for what we want to do here. But it really means the average, so for any x, the average length of the search path for x is about 2 log n plus a constant. So this means that if L0 had 1,000,000 elements in it, and I decide I want to look at the search path for any particular element, then its length will be about 40, maybe 43, 44, 46 on average. Okay. And that's because log base 2 of 1,000,000 is about 20. Could it be any probabilistic process instead of tossing a coin? Well, it has to be something that gives you a binary value. either promote it or don't promote it. So anything that gives a binary value, and if you use something other than a coin, like an unfair coin, then you don't necessarily get log base 2 of n here. Okay. So this log base 2 of n, we'll see when we do the analysis, it's base 2, that shows up because we're using a fair coin that comes up heads and tails with equal probability. If you do something crazy like instead you roll a 6-sided die and only promote it if it comes up 1 and you leave it below if it doesn't, then that changes this. All right, so this is this picture, and the ones that I can draw on the board are kind of misleading because they always look kind of squarish. But that example that I said with n is 1,000,000 is telling you that actually these things are not square at all. These things are very long and skinny, right? Because you imagine if you did this with 1,000,000 things, then you have n is 1,000,000, and then the height, you know, is something like maybe 46. So these things are really long and very short. In fact, not even. The height is not even 46. The height is even smaller. The height will be something like 20, 23. Because in the length of the search path, we're actually counting two kinds of steps. There are steps down and there are steps to the right. So the number of steps down we'll see is going to be about 23, and then maybe the number of steps to the right is another 23, in the case when n is 1,000,000. Okay. So proof. Next class. For now, let's see how we can use this to get to make some useful data structures. So the first data structure to think about is how we can use this to do a sorted set. And if you look in the book, you see that these things are referred to as S sets. So that's to distinguish them from the Java collections framework sorted set, which has all kinds of sort of crap sitting on top of it in its interface. S set boils it down to the three important operations, which are adding an element, removing an element, and those are obvious, and then there's finding an element, which does find the largest, not the largest, the smallest value that is greater than or equal to x. Okay. So these are really sorted sets. This is the essence of what they can do. Add things, remove things, and if I go looking for a value, find the smallest thing that's bigger than or equal to what I'm looking for. So if the value is there, if x is in the set, then give me back x. But if x is not in the set, give me back the first thing that comes after x. So the smallest thing that's bigger than x. Okay. And a lot of the things, other things you find in sorted sets, things like tail set and head set, they're just wrappers around these operations. Okay. So these are really the essence of these things. And so these are the things that we'll want to study. The other ones, they're kind of boring. Like the way headset and tailset work is they just make another simple data structure which contains one of these as one of its instance variables, plus a value x that says, if you ask me for something which is, like for instance, if you do tail set, if you ask me for something which is smaller than x, then I'll actually search for x instead. So it's just sort of boring stuff like that. Nothing exciting at the data structure level. It's just a wrapper around some other class. So these are the important operations: add, remove, and find. So important that I'll write them down here. Okay, so how could we, maybe it's just best if I erase all this. Okay, so now we're back to our clean looking list. So how can we implement a sorted set as a skip list? Well, it's sort of the natural thing that you would expect to do. The sorted set, the values in your sorted set, they live in the list L0. And what order are they stored in? Well, they're stored in sorted order. So for example, if I'm storing integers, and usually in my examples I'll use integers because integers are the easiest things for us as humans to look at two of them and say one is greater than or equal to the other, so we don't have to think about that. So, you know, we might have something like, maybe here is 5, 9, 10, 15, 66, 100, 105, 110, and 132. So these things live in the list L0 in sorted order. And the only exception here is the sentinel. And we can imagine the sentinel. If we need to think of some number being stored there, well, the number that's stored there is minus infinity. So then no matter what we have, what actual integers we have in our list, the one that comes before them, the sentinel, is smaller than the first one. So the whole thing, including the sentinel, we can think of that as being in sorted order. And although we won't implement it this way, we'll just imagine that those numbers also appear up in these nodes. Oops, forgot an arrow there. Okay. So, so far so good. This is what the skip list looks like for a sorted set. In this case, the sorted set contains 5, 9, 10, 15, 66, 100, 105, 110, and 132. Let's start with the first operation, the find x operation. And imagine that for this sorted set, I want to find the value 102. So I'm going to do that by following the search path for some node. And that means I'm going to start up here at the highest occurrence of the sentinel. Now, if I'm following the search path for a node, I need to know from here, should I go to the right or should I go down? Well, how would I make that decision? Well, I'm supposed to go to the right if it doesn't take me too far. So in this case, going to the right should happen if I see any number here which is smaller than 102, I should go to the right. So in this case I see 66, that's smaller than 102, so the search path goes to the right. Now here, if I look to the right, I don't see anything, I actually see null, so I should go down. But from here, if I look to the right, I see 132, so let me just write this down. 102 was bigger than 66, that's why I went to the right. But here, if I look to the right, 102 is less than or equal to 132, so I should not go to the right, I should go down. Here, if I look to the right, I see 100, and 102 is bigger than 100, so I should go to the right. Here, if I look to the right, I see 132 again, so I better go down. Here, if I look to the right, I see 105, which is too big. It's bigger than 102, so I would imagine that I would want to go down, but actually it's time to stop. Okay? So there's the end of the search path. Now, what am I supposed to do? I'm supposed to return the value. So this is supposed to return the smallest value bigger than or equal to 102. Where is that value stored? Well, look where the search path finished. It finished at a value which was smaller than 102, but the thing to the right is bigger than or equal to 102. Therefore, it's the small, because the things that are in sorted order, it's the smallest thing that's bigger than or equal to 102. Okay? So find 102 here will just finishes in some node in the list L0, and it returns the value stored at the right. Okay? So in this case, this returns 105, just by following this search path. How long did that take? Well, each step in the search path just involved a comparison, looking to see whether the thing we're searching for is bigger than the thing that's off to the right. And then we either go to the right or we go down. That only takes constant time. And this lemma says the expected length of the search path is at most 2 log n. So the find operation takes time that's proportional to the length of the search path for the node which is the answer, in this case the node containing 105. But this lemma says it doesn't matter. You give me any node, the expected length of the search path for that node is 2 log n. Now the only boundary case that happens here is if I do something like find 500, then you'll see that if I follow the search path for 500, it goes to the right, then it has to go down, then it goes to the right, then it has to go down, down, down. It finishes here at 132, and the general thing would be you return the next node in L0, but there is no next node. So why is there no next node? There's no next node because there's nothing in the data structure which is bigger than or equal to 500. So that's sort of expected. If you search for something that's bigger than anything in the set, then this doesn't have so the answer is not defined. So it'll return null or something. Okay? So add is somehow easy. Or not add, find is somehow easy. You just follow the search path. Let's try something that's maybe more challenging. What about remove? Let's take a skip list and try and remove something from it. Let's do that with blue marker. And let's actually try and remove $15. We want to remove 15 from this skip list. Again, we'll follow a search path. We'll in fact follow the search path for 15. And that means we start up here at the top occurrence of the sentinel. And we start searching for 15. So here we look to the right. We see 66, which is bigger than 15. So we go down. Here we look to the right and we see 15. So the rule for following the search path tells us that we should go down. But what we're trying to do, and that's what we will do. We will go down. But remember, what we're trying to do here is remove 15 from the list. Which means before we go down, we can actually get 15 out of this list L2. Right? L2 is a singly linked list. That means that this node here, in this case it's the sentinel, it has a pointer to the next node. And all we need to do to get rid of that next node from the list is change that pointer. So that it points to 66 instead of 15. Then we go down. And now the same thing happens. When I look to the right, I see 15 again. So this algorithm for finding the search path says you should go down, but before you do that, you might as well take the time to splice this thing out of the list. Like so. And now you get to go down to this node. Now the algorithm for finding the search path says you should go to the right because 5 is less than 15. Again, you should go to the right because 9 is less than 15. Again, you should go to the right because 10 is less than 15. But now, if I look to the right, I see 15, and the algorithm says that I should go down, but that's the end of the search path. But again, before I do that, because the thing that I see to the right is the thing I'm trying to remove, I should change this pointer so that it doesn't point to 15, but it points to the next thing. So now if I look at this picture, I'll see that, yeah, there are some nodes here with 15 in them, but nothing in the picture is referring to these nodes anymore. Right? The only things that used to point to 15 were this node, and this node, but they've all been changed to point to the next thing, which in Java means that the garbage collector will come along and take away all these occurrences of 15 because they're not referenced by anything. Okay. So that's how you remove something from a skip list. Follow the search path. Even if you did not have 102 in nodes, it returns the closest number. Yes, it returns the smallest value that's greater than or equal to x. It's not the same as the closest number. It's always going to return a value that's greater than or equal to. but it is the smallest one that's greater than or equal to. But I think you could easily, if you wanted the largest value, which is smaller than x, you can easily rework the code to do that. That just means finding the node. In fact, it's the value stored in this node, right? So in general, the step from the last node in the search path to the next one takes you to x or past it. That means the one before it was smaller than x. So what are the two closest values? It's always these two here. Okay, so removing from a skip list is easy. You follow the search path, exactly the same algorithm you always use, or the same algorithm you used in find, except you add an extra step, which is, well, every time the search path goes down, that means the thing to the right is the thing you're trying to remove, so remove it. Or every time the search path goes down and the thing to the right is the thing you're trying to remove, you should remove it. Okay. So in general, the thing to the right may not be something you want to remove. For instance, it didn't happen here, but from here, here, and here, each time the search path wanted to go down, that's because the thing to the right was the thing we're trying to remove. How long does that take? Well, the time that it takes is just how long it takes you to traverse that search path and then splice out a node at each step, which is 2 log n. And now, so that's 2 of the 3 operations. Like, easy. What about add? Well, let's say I want to add, and I will, just because I have space for it, oh no, let's make it hard. Let's say that I want to add $115. So that means that 115 is going to go there. Somehow I'm going to have to add it to the list in between 110 and 132. Not surprisingly, I'll start at the top occurrence of the sentinel, and I'll follow the search path for 115, and somehow that should do what I want to do. So let me just draw in that search path first, but I don't imagine following it yet, but just let me draw it in so we see what it looks like. It goes down here, it goes down here, it goes down here, and it goes down there. That's the search path for 115. Now, 115 is supposed to go here, but maybe 115 also has to go here, and maybe it also has to go here. Maybe it even has to go here. How do I decide that? Well, before I even start following the search path, I start tossing a coin. So I toss a coin, maybe it comes up tails, or maybe it comes up heads. If it comes up tails the first time, then I stop and I say, well, 115 is only going to live in L0. But maybe it comes up heads and then tails, in which case 115 will live in L0 and L1. Or maybe it comes up, maybe it even comes up heads 3 times in a row, and then comes up tails, in which case 115 will live in L1, L2, and L3. And maybe if I get really unlucky, it comes up 4 times in a row, in which case 115 will not only live in L1, L2, and L3, it'll live in a list L4, which doesn't even exist yet. So the trick is you do the coin tossing for this new value that you're adding, which is just tossing a coin, until the first time it comes up tails. The number of times it comes up heads tells you what the index of the highest list that it should live in. And in some very strange, or in less and less common cases, if the list is already big, you might find that actually the number of heads before that first tail is more than the number of lists you have, in which case all you have to do in that special case is to create some new copies of the Sentinel to make this thing high enough. After that, you start following the search path. So let's say I tossed the coins for this thing, and I got, let's say, heads, first toss, heads, second toss, and then tail. So this means, tail means live in L0 like everybody, but this means live in L1, and this means live in L2. So that says that we want to include this new value, 115, in all the lists starting from L2 onward. So we follow the search path for 115. First step that it takes is in L3, and it's a step to the right. Steps to the right are no problem. We just do those as we normally would. The next step is a step down. Now, it's a step down from L3 into L2. We've already tossed coins and decided that the new node that we're adding is going to live in L2 and below. And in particular, it's not going to live in L3, so I just go ahead and make that step down. Now I follow the rule again. The search path says, well, to the right of me is 132, which is bigger than 115, so I should take a step down. And before I do that, I see, oh, I'm currently in L2, and the new node that I need to insert needs to go into L2, because I've decided that by tossing coins. And if you look at where I am in L2, I'm at a node that is smaller than 115, and to the right of me is a node that's bigger than 115. So the new node has to go in between those two nodes. So it's at that point that you splice in 115. So this is just splicing something into a singly linked list. Now you can go down. The next step is a step to the right. You don't do anything special there. But now, before you take your step down, because you're in list L1 going down to L0, you need to add in 115. So you splice it in there. Take your step down. Now it's a step to the right, a step to the right. Here you would have taken a step down, but there's no place to go anymore, so it's the end of the search path. But before you finish, you need to add in that new node, 115, in between these two. Okay. So now you get 115 in all of the right places. How long did this take? Well, I had to toss coins. And the length of this thing, the number of steps that I took, is just the length of the search path for 115 in the new list. Okay. So at the end of this, I have a list which contains 115. It's a skip list. It has n+1 elements. So the length of this search path that I followed is just the log of, well, is given by this thing, except instead of n, you have n+1. So that's the easy algorithm for adding into a skip list. So that's it. Add, remove, find. Each of those operations is basically done by following a search path, in one case it's find is just following a search path, remove is following a search path and then possibly splicing out elements as you move down, and add is following a search path and possibly splicing in elements as you move down. All very simple, and I think all the kind of thing that you could walk away from here, and if in the next little while you manage to find yourself stranded on a desert island, you would remember enough of this to be able to reconstruct this and reconstruct those three operations. We'll see later in the course that some of the really classic data structures for implementing sorted sets, they don't have that property at all. So when we see red-black trees, we'll see that the rules for red-black trees are incredibly complicated. You don't stand any chance of actually memorizing those rules. You go and you look them up or work them out repeatedly. But with the skip list, this is really quite easy. Just remember the search path, and everything has to do with everything is done by traveling along this search path. Why is it log of n plus 1 again? It's log of n plus 1 because remember there's this possibility that we have to add, the easiest way to think of it is because we may have to, if we toss so many coins, if the coins come up heads enough times that it increases the height of the skip list, then, well, that means there's some work to increase the height of the skip list. And you may be worried about that work because we didn't count it. But actually, just look at the skip list that you have after you've done the add operation. It's a skip list with n plus 1 things. And the work that you've done to add x is just the length of the search path in that skip list that has n plus 1 elements, not the original n elements. So it has all the original n elements and x. Okay. And this, so I kind of made a bit of a fuss about it when I said, well, you can define the skip list by walking across L0 and tossing a coin for each one to see what gets into L1, or you can look at the individual elements and toss coins to decide how high they go. So when you implement this, when you implement a sorted set this way, you're taking the alternate view, which is, yeah, the way I did it was when it was time to add 115, I tossed its coin that many times to see how high it would go. But that doesn't change the shape of the list, or in fact, the distribution of shapes on the lists. The likelihood of getting any particular list is this after adding and removing things. If there's n elements in the bottom, it's as likely as if, it has the same distribution as if I had just built them by starting with L0 and building lists up. The nice thing about coin tosses is it doesn't really matter what order you do them, because they're independent of each other. Future coin tosses that I do now have no effect on the outcomes of ones in the future. So that's what we're using here. Okay. A couple of sort of implementation details. If you're really going to implement this, the good implementations don't actually create all these nodes. They create nodes that look like this. A node has a data item x in it, and it has an array of pointers to the next elements in the lists. That array always has length at least 1. So you can have data items that look, or skip list nodes that look like this, but in general, the number of these pointers is 1 more than the number of, so it's the length of this sequence here, heads, tails. So 1 more than the number of heads you get when you toss the coins to decide the height of this thing. So really, even though I've drawn separate nodes for 66, the picture really looks like 66 is there. There's 1, 2, 1, 2, 3, 4 occurrences of that, so that thing has 4 pointers coming out of it. The problem with when you draw pictures that way is that when you try and draw it here, is it looks ugly. Because these pointers don't really point to, you know, if I have another node over here whose height is 4, then this pointer, you know, I like to draw these things horizontally, so this is horizontal, but in actuality, it points to this node. And you just remember that you were at level 3 here, so that when you look at this node's pointer, you're looking at the right place in the array. Does L0 always start with tails? How would this change if your coin tosses were heads, heads, heads? Well, the coin experiment is you toss a coin. If it comes up heads, you take the node and you put it in the next list. So the node is always in L0. Toss a coin. If it comes up heads the first time, you put it in L1. If it doesn't come up heads the first time, you stop and you leave it in L0. So you just count the number of heads until the first tail, and that tells you how many extra lists beyond L0 you have to put it in. So here, heads, heads, tails means put it in L1, put it in L2, and then stop. Okay, so Yan Hui is asking why we returned, when we searched for 102, why we returned 105, because that's the definition of the find operation. It's gone now, but it's supposed to return the largest value, which is the smallest value, which is greater than or equal to x. Okay. Good. So that's one thing. And if you look at the code, which we might do a little bit later, you'll find that actually the add operation is implemented slightly differently than I've described. The add operation tosses the coins, creates the node, follows the whole path, and then adds it. It actually keeps the path on a stack and then adds it. Why is it implemented differently that way? Well, it's implemented differently because just the particular way that Java wants the find operation to work is, or not the add operation to work is, if the thing is already there, you should not start adding it. You shouldn't add it again. And the problem with the thing I just described is it's possible that if the thing was already there, you might try and start adding it before you realize that it's there. So for example, if I added 105, I might try and start adding 105 at this level, and it's not until I get down to the bottom that I realize I should not have done any of that. But that's just it's a small detail of the particular way in which this thing should work. Okay, so I said you could implement sorted sets, and in particular these fundamental operations from sorted sets. That's what the book calls the S-set interface. And I also said you could implement lists. Well, how would you implement a list? And well, what I said was that you can implement lists and have excellent performance. So let me draw a quick skip list. So again, you're going to do the natural thing. So if I want to implement the list interface, that means I want to represent a list using this thing, then I'll do the obvious thing, which is, my list items have indices, 0, 1, 2, 3, 4, and so on. So I'll look in this bottom list L0, and those will be the items in the list that I'm representing. So this first one is the one at index 0, this is the one at index 1, 2, 3, and 4. And, well, I guess that means that this one here, the Sentinel, which is not really in my list, but I can imagine that it has index -1. Okay. All right. So remember, the list operations are add x at position I, remove position I, and there's the get and set I. But let's just focus on get I. Set I is not really any different. So let's think about how we would do this, see why it's not obvious how to do it, and then see what we need to do to make it work. So, right, let's say I want to do something like get, in this example, get the list item at position 2. So that corresponds to this thing in L0. And since this is a skip list and we've seen that everything seems to be done using search paths, that suggests that we'll want to do the same thing here. Of course, we could start in L0 and just walk that many positions. In this case, it's only 2. But of course, walking through L0 L0 is just a singly linked list. That's going to be slow. In particular, if we ask for large values of large indices, we have to walk through the whole list. So we want to start up here and follow the search path. Now, how do you follow a search path? Well, you basically look to the right and say, is to the right too far or not far enough? If it is too far, you should go down. If it's not far enough, you should go to the right. Now, looking at the picture that we have here, we can see that, yeah, if you're trying to get to the node with index 2, you shouldn't go to the right. That's too far. But the computer, the algorithm, does not get to look at this picture. It has to use whatever information is available in this node. And in this case, in this node, there's not enough information available. Now, we know that when we start at the top occurrence of the Sentinel. So we know that we're somehow starting at a node whose index is -1. And what we would like to know is, if we go to the right, what index are we going to get to? So we add a little bit of extra information. Each node not only has a pointer to the right, but it has an integer which tells you the difference in indices between the index of this node and the node to the right. So this thing here, so it's stored at this node, but you think of it as being written on this edge. This node remembers that if I go to the right, that's an increase of 4 in the index, because -1 plus 4 is 3. Or if you like, what's the number written on this edge? It's the number of edges in the bottom list that are actually hiding underneath this one. 1, 2, 3, 4. Okay. So that means at this node there is 2. At this node there's 2. These edges here, it's 1, 1, 1, 1. So now, if that information is there, then I do have enough to follow the search path, right? I'm trying to get to 2. I'm currently at -1. If I take a step to the right, that's going to take me to 3. 3 is bigger than 2. I don't want that. So I'll go down. I'm still at -1. If I take a step to the right, it's going to increase my index by 2, which is going to take me to 1, which is smaller than 2. So I follow that step, and now I remember, I just crossed an edge, and we think of this as the length of the edge. The length of that edge was 2, so that took me to position 1. Minus 1 plus 2 is 1. Now again, I look to the right. I see that this is an edge of length 2 going to the right, and that's too much because 1 plus 2 is 3, and I'm only trying to get to the node at index 2, so I go down. And again here, I still know that I'm at index 1. If I go to the right, I will be adding 1, so that will take me to index 2, and that means that the search path for the node at index 2 actually would go down here or would end here. So using this information that's written on these edges, I can still follow the search path based on the index of the node. Okay. And stop. It'll it'll build the search path and stop just as before in the node in L0, which is just before the node that I'm interested in. Okay, so that's how get works. It uses this trick to follow the search path, keeping track of what the index of the current node is, and when it takes a step to the right, it has to increase that index. But it's always knows the index of the current node, then it knows whether it should take a step to the right. And it stops at this thing just before. And for the get operation, well, then it should return the value stored at the next node in L0. Okay. So that's the get operation. And now, how about the add operation? Let's try and do that quickly. Let's try and add at index 3, and let's put another x there, a green x. So that means we want to put that new green x there, but we want to do it the skip list way. So that means we're going to create a node that's going to go there, but also it might go in this list and it might go in this list. So again, we toss coins to decide how high it needs to go. And maybe in this case, we first get a head and then we get a tail. So that means that the thing should go in L0 and in L1. Now we start following the search path. So we're trying to follow the search path for 3. From -1, if I add 4, that's going to take me to 3, which is too far. Remember, I want to stop at the node just before. So the search path should go down here, but, well, okay, so it should go down here, and it will. So the search path goes down here and doesn't splice anything in because, well, because I already decided that this new node only needs to live in L0 and L1. That's what these two coin tosses did. So just go down and don't do anything. Now, from this node, if I go right, I will get to index 1, -1 plus 2. That's not too far. But if I continue, I'll get to index 3. That is too far. So the search path should go down. But before I go down, I should splice in the new value. Okay? So I need to splice in this new node that contains the green X. Now, that's easy enough to do. But there's something else we have to do here is, well, every edge in this picture now, every pointer to the right, has a length associated with it. I need to fix those lengths. How do I do that? Well, it's an easy calculation. Here I know the index of the node that I'm at. It's 1. I've been keeping track of that. I'm at the node of index 1. I just spliced in the node that will be at index 3 once I'm all done. So the difference between 1 and 3 is 2. So that goes there. That's what goes on this edge, and that's because I know that this node is at index 3. What goes on this edge? Well, I still know that this, that I was looking at this already, and the reason I didn't go to the right is because it took me to the node at index 3. The node which was at index 3 before, once I put this new thing in front of it, is going to be at index 4. So the value written on this edge should be the difference between 3 and 4, okay, which is just 1. And now the same thing happens. I keep following the search path for 3, which takes me here. And at this point, I would want to go down. I do that, but before I do, I splice in the new node. With the green X in it. And I need to write lengths on these edges, but I know what they should be because I've been keeping track of the index of the node that I'm at. It's 2. The index of the one I'm inserting is 3. So here should be the difference between those two, which is a 1. And the old node, the one that used to, the new successor of this node, used to be at index 3. That's going to jump to 4 because I'm inserting something in front of it. So here should be the difference between 3 and 4, which is another 1. So inserting a new node at any index is just a matter of following the search path, tossing some coins, following the search path, doing some splicing in, and then just making sure you get the right lengths on these edges here. Sort of an easy calculation to work out. And then the final thing is remove, which is again not hard. I mean, you can imagine what it looks like when you want to remove, for instance, this node. You follow the search path. When you see it off to the right, you remove it. The length of this edge is now this number plus this number minus the one that I removed, so it becomes 2. And then the same thing. At this point I need to remove it. The length of this edge is this number plus this number minus the one that I removed, so the length is actually just 1. So again, all of these operations, adding and removing at a particular index, take time that's proportional to the length of the search path, and next class will prove that this search path, the expected length of it is at most 2 log n plus a small constant. Okay, that's the end of the lecture today. I'll answer a couple of questions. I see that there's some that built up here. Do the lists L1, L2, etc. have indices as well? Well, we don't explicitly store any of the indices. So, I mean, when we're thinking about this, L0 has the indices 0, 1, 2, 3, and 4, but that's just for us to think about it. Those indices are given by the order in which things appear in the list L0. What are we storing explicitly? We're explicitly storing these so-called lengths of these edges. which tell us if I go from this node to this node, how much does the index change? So that implicitly means that I can figure out what, if I'm currently at a node at this index, in this case it's -1, and I cross this edge, then the index of this one, really in the bottom list, is -1 plus 4 is 3. So we don't imagine these things as having indices 0, 1, and 0, 1, 2. That's not really useful for us. Wouldn't we also need to shift back the elements and change the indices after remove? No, we don't. With these indices here, they're just for us to remember. They're not stored at all in the structure. What's stored in the structure are the lengths of these edges. At the bottom list, they all have length 1. At the upper lists, they have length which is equal to the number of, let's say, edges in the bottom list that are below them. So this one has 2 edges of the bottom list below it, so its length is 2. This one has 4 edges of the bottom list below it, its length is 4. And you see some patterns developing that I don't even need to know that the length of this is 4. I didn't need to look all the way in the bottom list and count edges. I can see that below it in the next list are 2 edges of length 2. So there's no, the indices in the bottom here, they don't exist. We just get to them by using these. So in memory, this thing ends up looking like, and we'll see this, a node has sort of, it has a data value, it has an array of pointers, and it has an array of lengths, like 1 for the pointer in the bottom list, maybe 2, maybe 3, maybe 5, maybe 9. The lengths are always, well, they're not getting shorter, because that in memory, the way when I write a number on an edge like this, that really means it's inside the node and it's tied to that particular location. So this is the edge in L0 has length 1, the edge in L1 has length 2, the edge in L2 has length 3, the edge in L3 has length 5, and so on. Yes, Hamza, you're right. So I skipped over that. When you go down in the upper lists, I knew I was forgetting something. So when you take a step down in a list that you're not going to insert to yet. So for example, when I was adding here, I was putting a new thing in these 2 lists. Before I took that step down, I should have increased this by 1. Why 1? Well, because I'm going down, that means the new node is going to appear underneath this edge, and that means there's 1 more node in the bottom list under this edge, so the length of this edge increases by 1. Good catch. How does sset_add handle duplicates? We'll take a look at the code next class, but what it actually does is follows the search path, keeps these nodes where it turned down, so that's these ones. It keeps them stored in an array, and by the time it gets to the end, then it has determined whether or not the node is already there. So by the time it gets to the end, if this is not the value that's being added, it's because it's not there yet. Then it just does the splicing in by using the values in this, using these stored nodes in this array. So it just walks back up. If it inserts, and if it follows the search path and finds the value already there, then it doesn't have to do anything. The value is already there, it doesn't need to add it. So that's the extra complication added by the fact that you don't want to insert duplicate values, and yeah, that's the main idea. Okay, good. Glad you guys enjoyed this. So there you go, one nice simple data structuring technique that lets you implement sorted sets and lists with a really fast access time for any of the elements in the list. So this is, at least for things in the middle of the list, this is way faster than any of the implementations we've seen so far. I mean, at best we get things that are fast, that have the min of I and n minus I. That's the best we've seen so far. Now I don't care about the value of I, it's just log n no matter what. All right. So I'll see you on Friday then.